This video will focus on the Ready, Set, Go problems from Unit 8, Lesson 3. In the Ready section, you're finding the greatest common factor for each of the given number pairs. We can find the greatest common factor, or GCF, by listing all the factor pairs for each expression and finding the greatest number or factor they have in common. We can also use prime factorization by creating factor trees, which lead us to the prime factors of each number. Once we have all the prime factors of each number, we multiply the ones they both have in common to give us the GCF. For a review of prime factorization using factor trees, please refer to the RSG video for Unit 6, Lesson 7. Now let's look at an example with algebraic expressions. Again, we will list the prime factors of each and look for the factors they have in common. In this example, they both have the factors 2 and x. The GCF of these two expressions is 2x. In the set section, you're factoring polynomials by rewriting each given expression as a product of two linear factors. In the previous lesson, we worked on factoring polynomials with leading coefficients of 1. In today's task, we developed the use of an area diagram to support factoring polynomials with leading coefficients other than 1. The first factor, 2x plus 1, represents the top side of the entire rectangle. The second factor, x minus 2, represents the left side of the entire rectangle. Remember, the red tiles represent negative numbers. Now that we know the dimensions of each of the squares and rectangles, we can fill in the areas by multiplying the length and width of each. Finally, we will simplify by combining like terms, and we will find that the area of the rectangle, of the entire rectangle, is 2x minus 3x minus 2. We can use the distributive property to check our work. Now let's look at an example like the problems in your workbook. In this example, we're given the polynomial in standard form. We're being asked to write the two linear factors. Let's use the area model to help us. Remember, the area model must always create a rectangle. The first term in this trinomial is 3x squared. We know that we need to have three large squares, each with a dimension of x by x. The second term in the trinomial is 4x. We know that we need to have four rectangles with dimensions x by 1. The third term in the trinomial is 1. We know that we need to have one small square with dimensions 1 by 1. If we place three of the four rectangles along the bottom and the last one along the right, we can fill in the bottom right-hand corner with the small square. Now our model has the dimensions 3x plus 1 and x plus 1. We can multiply the first term of the first factor, 3x, by the second term of the second factor, 1, to get 3x. This is represented with the three rectangles along the bottom of the model. When we multiply the second term of the first factor by the first term of the second factor, we get 1x. This is represented with the rectangle along the right side of the model. Those combine to give us the 4 x's found in our model and in our trinomial. Let's look at another example. The first term in this trinomial is 2x squared. we know that we need to have two large squares, each with dimensions x by x. The second term in the trinomial is negative 10x. We know that we need to have a value of negative 10 rectangles with dimensions x by 1 once we combine all the rectangles together, or x by negative 1. Remember that one positive rectangle and one negative rectangle will create a zero pair and essentially cancel out each other's value. The third term in the trinomial is 12. We know that we need to have a value of 12 small squares with dimensions 1 by 1 once we combine all the small squares together. Now we must figure out how to use these tiles to form one large rectangle. Notice that we have formed two rectangles already using the large squares and the rectangles. Each of the rectangles we formed already have dimensions x by x plus 4, and each with an area of x squared plus 5x. If we divide them into two groups and we split the small squares into the two groups, we would have 6 of the small squares in each group, but we cannot add them to the models to form complete rectangles. When we move a rectangle from the bottom of each model to the right side of each model, we see that we can fill up the empty spaces with 4 of the small squares, but that still leaves 2 small squares left over for each group. When we move another rectangle from the bottom of each model to the right of each model, we see that now we can completely fill in the empty spaces with the small squares. Now we have 2 of the models, each with dimensions x plus 2 and x plus 3. We can check our answer by using the distributive property and combining like terms. Notice that the GCF, or greatest common factor, of 2 from the standard form of the equation is factored out when written as the product of linear factors. In the Go section, you're evaluating exponential functions in context. In this example, we're looking at the growth of bacteria B represented on the y-axis over time t, represented on the x-axis. Let's explain the values of this exponential function in the context of the problem. B of 0 means that we're looking for the initial bacterial growth. We can see from the graph that when no time has passed, the bacterial growth is 1. B of t equals 4 means that we're looking for the day, or the time, in this case it's in days, when bacterial growth is 4. We can see from the graph that on day 2, the bacterial growth is 4. Let's look at another problem. Here we're being asked to find the rate of change on the interval 0, 3. Remember that the interval is represented by the x-axis, and the brackets mean that the values of 0 and 3 are included in the data set. We see that the part of the function represented by this interval is from the point 0,1 to the point 3,8. The rate of change would be the slope of a line that would connect the 2 points. When we divide the difference of the x values, when we divide the difference of the y values by the difference of the x values, we find that the rate of change for this interval for the interval of this function is 7/3. Let's look at one more problem. Here we're being asked to find the rate of change on the interval 2, 3. Remember that the interval is represented on the x-axis, and the brackets mean that the values of 2 and 3 are included in the data set. We see that the part of the function represented by this interval is from the point 2, 4 to the point 3, 8. The rate of change would be the slope of the line that connects those 2 points. When we divide the difference of the y values by the difference of the x values, we find that the rate of change for this interval is 4.